Chapter 15 talks about dynamic force analysis. Two methods are introduced here, free body diagrams and the conservation of power. These two methods are frequently applied to solve static force analysis and dynamic force analysis. We will talk the method of free body diagram first. We use dynamic equilibrium equations to solve dynamic problems. This slide shows you what dynamic equilibrium equations are. In fact, they derive from Newton's second law. Newton's second law states the relationship between force and motion that is central to the study of kinetics. Newton's oral equations describe the translational motion of a rigid body. It states the sum of all external forces acting on the body is equal to the body's mass times acceleration of its mass center G. And the oral equation describes the rotary motion of the body, where summation mg is the resultant moment of the force system acting on the body about the center of the mass. Ig is the moment of inertia. It is a matrix based on coordinate axes x, y, z, and with an origin at the center of mass. And alpha g is the angular acceleration of the body related to that same fixed frame. If we introduce a force Fi equal to minus n times Ag, we call the inertial force, which is applied on a line passed through the center of mass, and a couple Ci equal to minus Ig times alpha g, called the inertial torque. Inertial force and the torque are imaginary force and torque supposed to act upon an accelerated body. They equal in magnitude and opposite in relation to the resultant of the real forces and the torques. We can treat the inertial force and the inertial torque in the same way as any other external force and torque. Then the dynamic equilibrium equations assume the same form as the static equilibrium equations. It looks like we move the kinetic items NAG and IGRG from the right side of motion equation to the left side. Therefore, we can convert the dynamic equilibrium equations to the same form as the static equilibrium equations. It is called as D'Alembert principle. The rigid body is subject to general plane motion caused by the externally applied force and the couple moment system. The translational motion have two balance equations relating to component x and y, and the rotational motion has one balance equation about center of mass G. So we have three independent scalar equations for the general motion of the body in the xy plane. The relationship between the mass and the weight is given here. For the metric units, mass is kilogram, weight is Newton, and the gravitational acceleration is meter per second square. And for the imperial units, mass is slug, weight is pound-foot, and gravitational acceleration is feet per second square. We use moments of ignition for calculating initial torques. Moment of ignition is defined as the integral of second moment about an axis of all the mass elements, the n. The moment on r is the perpendicular distance from the z-axis to arbitrary elements, dn. The z-axis always passes through the center of mass G. In the textbook, sometimes the problem gives the radius of gyration k. We can use it to compute the moment of ignition. The body's moment of ignition is determined as n times k squared. By the way, you do not need to worry about determining moments of ignition, because they will be given in most of the problems. The general procedure for solving dynamic equilibrium problems is to solve the position, velocity, and the acceleration kinematic of the system using the procedure of Chapter 4, 5, of 7 to obtain the acceleration of all the bodies with significant mass and get the angular acceleration of all the bodies with significant ignition. Chapter 4 and 5 use the graphical method to determine velocity and accelerations. We do not teach them in this course. Well, if you are interested, you can study by yourself. Compute the initial force and the torque acting on each body according to D'Alembert's principle. Apply the initial force and the torque as an external force and the torque to each member. Drawing a free body diagram of each member, including all external forces acting on the member and all reaction forces from other members to which it is connected. Finally, use a math tool to solve the equations for the unknown forces. It may be seen that the last three steps in the process are identical to the solution of static equilibrium problems. This problem is example 15.4 of the textbook. We need to find the driving torque that must be applied to crank member 2 to maintain the constant angular velocity of 16 rpm in the clockwise direction. This mechanism moves in the horizontal plane. Therefore, the weights of members do not affect the motion. Only dynamic forces need to consider. In this case, we neglect the weights of members 2 and 5, so both members have no initial load acting on them. Members 3, 4, and 6 have initial loads. We need to solve the angular accelerations for initial torques and the accelerations at centers of mass for initial force. In this case, members 3, 4, and 6 have initial loads. We have angular velocity omega2 with a constant 16 rpm. It gives angular velocity omega2 equals 2 pi radians per second, and the angular acceleration r2 is 0. Therefore, from acceleration analysis, we get the angular accelerations of r3, r4, and r6. Then the accelerations of ag3, ag6, and ab can be figured out. They are vectors and have each magnitude and duration. Then initial force of members 3, 4, and 6 can be determined like this. In the imperial units, the mass equals the weight divided by the gravitational acceleration, 32.2 feet per second square. So the length unit in the acceleration should be changed from inch to feet. All accelerations are divided by 12. We can obtain initial force Fi3, Fi4, and Fi6 equals 0.056, 0.036, and 0.026 pound-force, respectively. We know each initial force is opposite in the direction of acceleration. We have radius of gyration of members 3, K3, and member 6, K6. The moment of inertia can be determined by the mass times the radius of gyration squared. Here, we need to convert the unit of the radius of gyration from inch to feet to determine the initial torque. Now, the unit of the initial torque is feet pound-force. We change the units back to inch pound-force for equilibrium equations. Here, member 4 have no initial torque because member 4 cannot rotate. Its angular acceleration is 0. Now we draw the free body diagrams of all members. For dynamic force analysis, the initial forces and the initial torques are applied as external forces and the torques to the members. They are added into the free body diagrams of members 3, 4, and 6 like this. In this step, we write dynamic equilibrium equations for each free body diagram. Let us start with member 2. There are two reaction forces, Fa and Fa star, and the torque T acting on the member 2. We write two force balance equations in x and y components, and write a moment balance equation about point A star. According to the geometry, the distance A star is 1.5 inch. So we have the moment on XA equal to 1.5 times cosine of 6 degrees, and YA is 1.5 times sine of 6 degrees. Then substitute those values into the moment balance equation. We can get this equation. Moving to member 3. In this case, inertial force Fi3 and the torque Ni3 are involved. So we have four forces and a torque acting on this member. Breaking those forces into x and y components, we write two force balance equations like this. And write a moment balance equation. This time, we choose center of mass. G3 moments are taken. It will slightly simplify the equation since it eliminates Fi3. All the values of moment arms are shown in this figure. We can substitute them into the moment equation to get the equation. We are continuing with member 4. Only initial force Fi4 is involved, so we have four forces and a moment. Two force balance equations are written like this. And we write a moment balance equation about point B. Now, moment N14 equals to 0 because all forces pass through point B. Because member 5's mass and the moment of inertia are neglected, so no inertial laws are involved here, we can see member 5 is a two-force member. Both forces Fc and Fd are the same in magnitude and aligned and opposed along the axis of the member. We write a moment balance equation about point D. The length of member 5 is 2.25 inches, so we get this equation. Finally, for member 6, inertial force Fy6 and torque Ni6 are involved. So we have three forces and a torque acting on this member. We write two force balance equations in x and y components. And write a moment balance equation about point D star. Then substituting the moment arms into the moment equation like this. Now we have 14 unknown forces and 14 equilibrium equations. T, Fa star x, Fa star y, and so on. These equations can be rewritten into a system of linear equations. Then we can use a math tool, for example, Mathematica, to determine the unknown forces. I suppose most of you are difficult to get a math tool. So for dynamic force analysis, you only need to write the equilibrium equation of each member. In other words, you don't need to solve this equation set. Three examples are used to describe the free body diagrams for dynamic force analysis in detail. The first example is a 4-bar liquid. A motor drives the crank linked to rotating at an angular velocity omega2 equals to 2 radians per second, and the angular acceleration alpha2 equal to 3 radians per second squared. There are two input torques, tau 2 of 200 Nm acting on link 2, and tau 3 of 20 Nm acting on link 3. When the masses of the links are too big to ignore, their weights need to be considered. They are 20, 30, and 25 Newton for links 2, 3, and 4 respectively. And the moment of inertia of each link is given. They are 0.2, 0.3, and 0.25 Newton kilogram meter square for links 2, 3, and 4. All the positions of joints and the centers of gravity of links are known and represented in coordinates. This problem is to find the output torque tau 41. First, we use the closure equation for velocity analysis to determine angular velocity of link 3 and 4. The angular velocity omega2 is given as 2 radians per second. Then angular velocity omega3 and omega4 are figured out as -1 and 1 radians per second. Then we use the closure equation for acceleration analysis to determine angular accelerations of link 3 and 4. The angular acceleration alpha2 is given as 3 radians per second square. Angular acceleration alpha3 and alpha4 are figured out as -0.5 and 4.5 radians per second squared. This slide shows you how to compute the velocity at the center of mass, and their results for your reference. Actually, in the method of free body diagrams, the velocity of points are not involved, but for the method of conservation of power, they will be used. And this slide shows you how to calculate accelerations at centers of mass and their results. For dynamic force analysis, we introduce initial forces as external forces acting on the member. Therefore, we cover the dynamic problem into the static one. To determine the inertial forces of members, the accelerations at the centers of each member's mass must be figured out. We have accelerations at the centers of mass, so the initial force can be determined by the mass n times the accelerations a, and the direction of the initial force is opposite to the acceleration. In a metric unit system, the mass equals the weight divided by the gravitational acceleration, 9.81 meters per second squared, and the initial force unit is Newton. Since the moments of initiation are given, the initial torque can be figured out by the moment of initiation I times the angular acceleration alpha. E has also a direction opposite to the angular acceleration. The equilibrium equations are similar to the previous example of the static problem, but for the dynamics problem, initial force and the torques must be added into 3 equilibrium equations. In member 2, we add the initial force Fp and the initial torque Cp into the free body diagram. For convenience, we assume the x and the y components of initial force Fp always are positive, and the initial torque Cp is in the counterclockwise direction, so it is positive too. Then, initial force Fp and the initial torque Cp are added into 3 equilibrium equations like this. They are colored as red. Then we substitute known values to the equations to complete the equilibrium equations. For example, for Fpx, we give a value of 2.041. Fpy is 1.02, and the Cp is minus 0.6. This slide shows you the dynamic equilibrium equations of member 3. Again, initial force Fh and the torque Ch are added into free body diagrams and the 3 balance equations. And this shows you the dynamic equilibrium equations of member 4. Initial force Fq and the torque Cq are added into the equations. If we want to solve the equation for unknown forces, we need to prepare a system of equations from the equilibrium equations like this. The substituting all known values into the equations, we can use a math tool to solve unknown forces. The results are listed here for your reference. Because all the forces and the torques are input log here, we need to flip the direction of input torque tau 14 to get the output torque tau 41. It is 366.8 Nm in the counterclockwise direction. The following two examples are a slider crank mechanism and a double slider mechanism. The procedure for solving two examples is similar to those measured in example 1. In this slider crank mechanism, we need to find the input torque Taiwan 2 under the given condition. We do the velocity analysis like example 1 to get angular velocity omega 2 and omega 3. And then the acceleration analysis is performed to determine angular acceleration alpha 2 and alpha 3. Substituting the angular velocity into velocity vectors, we can get velocities of center of mass Vp, Vh, and Vc. And substituting the angular velocity and the accelerations into acceleration vectors, we figure out acceleration of centers of mass AP, AH, and AC. Since we have masses, momentous annihilation, accelerations, and angular accelerations, we can get initial forces and the torques of members 2, 3, and 4. Here, initial torque of member 4 is 0 because it cannot rotate. That causes angular accelerations equals to 0. This slide shows you the dynamic equilibrium equations of member 2. Initial force Fp and the torque Cp are added into free body diagrams and the three equilibrium equations. And this shows you the dynamic equilibrium equations of member 3. Initial force Fh and the torque Cp are added into the equilibrium equations too. This is for the dynamic equilibrium equations of member 4. Here, only the initial force Fc is added into the equations. You can also choose this point C as a moment reference point. The moment M14 will be equal to 0 because all the forces pass through a common point C. 9 equilibrium equations are rewritten into a system of equations in matrix form, and substituting all known values into the equations, we can get unknown forces using math software. This slide shows you the results. We get output tau21 is 62.6 Nm in the counterclockwise direction. This example is a double slider mechanism. We need to find the output force F41 according to the given conditions. We use the closure equation of velocity to solve velocity of blocks moving along link 2 and the slope. Here, the angular velocity omega 3 is equal to omega 2 because the angle between links 2 and 3 is constant. And use the closure equation of acceleration to solve accelerations of blocks moving along link 2 and the slope. The angular acceleration alpha 3 is also equal to alpha 2. Then substituting known velocity and the angular velocity, we determine the velocity of centers of mass Vp, Vc, and Vb. and substituting known velocity and accelerations. The accelerations or mass centers of mass AP, AC, and AB can be determined. According to accelerations and angular accelerations, we can compute inertial forces Fp, Fc, and Fb, and the inertial torque Cp, Cc, and Cb. Here, the inertial torque of member 4 is 0 because R of 4 is 0. This slide shows you the dynamic equilibrium equations of member 2. Inertial force Fp and the torque Cp are added into the three equilibrium equations. This is dynamic equilibrium equations of member 3. Inertial force Fc and the torque Cc are added into the equations 2. And this gives you the dynamic equilibrium equations of member 4. Only the inertial force Fb is added into equations in this case. And the moment M14 is 0 because all the forces pass through point B. A system of linear equations in matrix form is shown here. We can write it according to the dynamic equilibrium equations. And substituting all known values in the equation set, we can solve 9 unknown forces. We get output force F41 equals to 3,113.2 Newton to the left, where the procedure for solving dynamic problems are similar to those for solving static problems. The difference is inertial effects play a role in the dynamic analysis, but the static analysis does not. Therefore, we know inertial forces and the torques are essential to solve dynamic force analysis